Well, first of all, it's a pleasure to be invited to give this talk. Actually, an honour to give the Kaiser public lecture. So thanks for inviting me. What I'll talk about today is SETI, the search for extraterrestrial intelligence. I'll talk about it generally, but in particular I'll talk about being able to detect advanced civilizations, because it's actually very difficult for us to detect civilizations like our own. The impact that we have in our environment here is actually quite limited. We expect that advanced civilizations, the impact on their environment might be much larger. And so the signatures that they leave might be easier to detect. So I'll talk about advanced civilizations, I'll talk about the results that we have so far, and also a little bit about what the implications might be of those results. I think they're kind of profound. I think SETI is a research topic that actually touches many different parts of science and can be actually fundamental to understanding how advanced we are ourselves in terms of the science that we do, and perhaps also more generally our culture. So what I want to do is to begin by describing what an advanced civilization might be, or at least what we think an advanced civilization might be. And I think many of you will probably actually know this classification. It's very famous. It was first proposed by this gentleman, Nikolai Kardashev. He's a radio astronomer in Moscow. And he proposed a classification of civilizations based on the amount of energy that they used, or the amount of energy that was available to them. He's still, by the way, very active in radio astronomy, and still going very strong. And so there are, well, Nikolai proposed three levels of civilization, the first being a type 1 Kardashev civilization. And basically, with the type 1 civilization, you have the availability of all the energy that's associated with your planet. Now that doesn't just mean the fossil fuel energy or the nuclear energy, for example, that you might be able to produce. It's basically dominated by the biggest energy source in our local environment, which is the sun. So it's defined as essentially the amount of energy, the radiant energy coming from the sun that falls on the earth, is absorbed by the earth. In principle, we could use that energy for our own purposes. So that's what a type 1 civilization is. And it has a sort of energy usage of around 10 to the 15 watts. So that's quite a large energy usage. It's much larger, for example, than what we use here for our civilization. We are about 10 to the 12 watts. So much less than a percentage of what the definition is of a type 1 civilization. Having said this is very much a non-linear scale. The Kardashev scale is very non-linear, as we will see. And so our own civilization is actually considered to be a type 0.7 civilization, even though we're actually very far away from this kind of being able to access this amount of energy. So that's a type 1 civilization, already pretty much more advanced than we are, at least in the sense of the energy that's available to it. Then you have the Kardashev type 2 civilization, and that's defined as a civilization that can basically access all the energy associated with its local star. And it's often associated with the work that this gentleman did, also around the same time as Kardashev was making this scale, and that is the Dyson sphere, the idea that perhaps you could surround the sun or the star with a sphere that would collect all the energy from that star, or in our case from the sun. It turns out that it's very difficult to build a sort of single solid surface to be able to do this, but you could have multiple, for example, solar collectors in orbit around the star that would collect a substantial fraction of the energy output of that star. And so the value here is basically the value of energy that's available to this civilization is essentially the luminosity of the star, or a typical main sequence star like the sun. And note that this is very non-linear, so I should have said 10 to the 15, that's a very big number, that's a 1 with 15 zeros after it. So here, this is an even bigger number, this is a 1 with 26 zeros after it. So very much a non-linear scale between the type 1 and type 2 civilization. And then you have the type 3 civilization, which is kind of like science fiction in a sense, and that is a type 2 civilization that is able to harness all the energy associated with the total stellar output of a galaxy like our own. So again, with 10 to the 37 watts, again another factor of roughly 10 between the type 1 and the type 2 civilization. So I heard someone say that it's all science fiction. It is all science fiction at some level, but it's actually a nice way of being able to understand what the different signatures might be of these different types of civilizations, depending on their energy use. So what do we already know in terms of SETI research? Well, I think one important thing that we know now, which we didn't know when people started to embark on SETI research some 50 years ago, when Frank Drake started to try and look with a radio telescope for artificial signals from the nearby stars. One of the things that we know now, which we didn't know even 10 years ago, is that there are many millions, tens, probably hundreds of millions of planets in our own galaxy that probably sit in this habitable zone in which there is the right conditions for liquid water to be on the surface. That there are many of these planets, and they are probably suitable hosts, as far as we understand it, for the development of life. Now, when I say that as a stupid astronomer or a stupid physicist. I don't really know anything about biology, and some biologists will say that perhaps life is actually a very rare event, or a combination of rare events. But at least we can definitely say that there is a kind of laboratory, if you like, and many of them throughout the galaxy, where in principle there are conditions similar to what we had on the Earth, where life could arise. So this is certainly good news for SETI researchers, and I think it's actually one of the reasons why there's really an upsurge in interest in SETI research, and a lot more astronomers actually doing SETI and actually writing SETI-related papers. And one of the reasons that we know so much about planetary systems in our own Milky Way is being able to extrapolate what we've detected with the Kepler spacecraft. This is a spacecraft that's been looking at a patch of the sky, looking at around 150,000 main sequence stars, so stars like our sun. They're looking for occultations by planets that just happen to be on our line of sight and in the orbital plane of these stellar systems, where we see a dimming of the brightness of the star because a planet is passing in front of it. And so Kepler has, as I'm sure many of you know, actually discovered several thousand of these exoplanetary systems. And we can extrapolate this to say something about the type of planetary systems that we might see throughout the Milky Way. In any case, this is a very nice movie that shows all of these different systems. Again, you've probably seen this many times before, but I think it gives you an idea of just how far we've come in understanding planetary systems. I'll come back to these planetary systems later on in the talk, and how they compare to our own solar system. Okay, what do we also know, and we've known it for some time, and which is not good news for SETI researchers, is that the Milky Way is incredibly big. I mean, it's the type of distances that are basically incomprehensible for humans to really fully appreciate. And not only is it big, but it's also very old. So the Milky Way has been evolving for billions and billions of years. And of course, life has arisen on this planet over the last 3.5, 4 billion years. So the Milky Way is big, but also the Milky Way is very old. And that has some implications for SETI research. So if you have two aliens here at either side of the Milky Way, or any other galaxy for that matter, then the distance across a galaxy of this size is something like 100,000 light years from one edge to the other edge. And so if this alien, if she sends a signal, then of course the electromagnetic waves that at least we are familiar with, they travel at a finite speed. They travel at the speed of light, 3 times 10 to the 8 meters per second. So it takes 100,000 years for a signal here to cross to the other side of the galaxy. So the distances involved are enormous, especially this becomes a problem for SETI research if intelligent life is actually quite rare. It may happen often, but if it's actually a fairly rare event, because of the distances involved, it's actually something that's very difficult to detect on civilization. Okay, and just to make this point, you see not our galaxy, but a galaxy that's a bit similar to our galaxy, and here we are around here in one of the outer spiral arms. And this little blue dot, which I hope you can see here, that shows you the expansion of our own signals, the radio waves that we've produced since the time of Marconi, for example. They've only traveled 100 light years out into space. So the region in which they occupy is tiny compared to the overall extent of the Milky Way. So it's very unlikely, for example, that our own signals have been detected by any other civilization. They would really have to be on our cosmic doorstep to be able to even receive those signals, never mind actually detect the signals. So this SETI problem is pretty difficult. And of course, if you actually want to communicate, then that's even worse, because not only do you have 100,000 light years this way, but then you have 100,000 light years in the other direction. And so that brings up an interesting point, which I think is crucial to the whole SETI discussion, and that is if you want to have a sort of SETI communication, then it means that the longevity of this civilization has to be 200,000 years old. That advanced technological civilization has to be around for 200,000 years before it gets an answer from some other civilization on the other side of the Milky Way. We'll come back to this again, but the longevity of a civilization, I think, is very important in terms of the frequency of intelligent life in our own Milky Way or any other galaxy. And, well, this terrible animation tries to make the point that we can have actually a lot of intelligent life in the Milky Way, but if the longevity of the civilization is actually very short, if it's 10,000 years, for example, then the overlap between these civilizations in time, not to mention space, but in time, is actually minimal. And so you never have two civilizations active within the same galactic system. Of course, if you have civilizations that do have very long periods where they exist, then the situation is different. And another problem about the distance is that even if you have very strong signals being sent out by this alien, by the time they've traveled 100,000 light years, they're very, very faint. Right? The intensity of the signal drops off as the square of the distance, so very, very quickly. So by the time it reaches here, even a very strong signal here is actually very difficult to detect, even with the largest radio telescopes that at least our civilization has. Well, this is just an example of some of the radio telescopes, for example, that we use to try and detect these signals. And in particular, I want to point out this resurgence in SETI research. Perhaps some of you have heard about the Breakthrough Listen initiative. This is an initiative by Yuri Milner. He is a Russian-American billionaire, and he has put $100 million into SETI research over the next 10 years. And these are some of the telescopes that he and his team are using to try and detect these very faint signals. So the Ring Bank telescope and Parkes telescope. Arecibo has been active in SETI in the past and probably in the future. And this is a new telescope, for example, the 500-meter telescope that is being built in China at the moment, which will also be used for SETI research. So there's a real resurgence in interest by researchers in SETI, and partly also bolstered by this recent initiative. Here in the Netherlands, I should point out that we're also doing some SETI research. So we have a PhD student, Emilio Enriquez in Nijmegen, and he's using LOFAR to look at the nearest star. Again, the nearest stars, because the signals are expected to be so faint. He's looking at the nearest stars to see if he can find artificial signals coming from these. It's a bit of a long shot because of the sensitivity issues, but it's certainly an interesting project, and I think in the future we can actually do much better, and I'll come back to that later on. So as far as we are concerned, it's actually quite difficult for us to detect certainly type 0.7 civilizations. So for example, our own civilization, it would be very difficult for us to detect the radio signals that we send out or the other signals that we send out, even if that system is on our own doorstep. And this is one of the reasons that I want to focus on advanced civilizations, because the expectation is that they use much stronger signals because they communicate over, for example, much larger distances within their own civilization. But it's worth knowing, and it perhaps tells us why SETI research has not yet had a positive result, is that even type 1 civilizations are relatively difficult to detect with the level of technology that we ourselves have as a type 0.7 civilization. So most of my talk I'm going to focus on type 2 civilizations, type 3 civilizations, but I will come back to type 1 civilizations towards the end of the talk. So, are these civilizations possible at all? Is it just science fiction? I think, personally, there's no reason in terms of the physics involved, and no reason in terms of how we project our engineering capabilities for advanced civilizations like type 2s, for example, to exist. There's no reason why these civilizations could not exist. If you see, particularly over, I think, the last 10 years, the advances that are being made here on Earth, especially in this area of 4D printing, of robotics, of drones, things which were essentially static in many ways for the past 100 years. All of a sudden, we're making large advances in engineering, not engineering on the large scale, but engineering on the small scale, and nano engineering, which I think is very important, and I think gives us a good chance of being able to realize actually the construction of very large infrastructures in space. The other question is, of course, if you want to be a type 3 civilization, then you don't only have to be a type 2 civilization, but you have to be prepared to actually colonize other stars in the Milky Way. So you have to be able to get at least to the nearest star, which means if you want to do it in any reasonable amount of time, you have to reach velocities which are not a significant fraction of the speed of light, but some fraction of the speed of light. And in fact, we've done pretty well. Even with chemical rockets, we are reaching relatively large, well, not large, but not so substantial. But we certainly get to speeds, and we could go even faster, for example, if we have stellar assists or binary star assists, we could get to something like 0.01 C. And in fact, that's more than enough for us to be able to colonize the Milky Way in timescales of much less than 100 million years. And one of the reasons, that sounds a long time, okay, but the galaxy is 13 billion years old, or 10 billion years old, so it's actually nothing. And it's of order a galactic rotation, so it's nothing in terms of the age of the Milky Way. And not only that, but just because there's a dispersion of velocities in the stellar disk of every galaxy, so you don't need to go to every star, you just need one civilization to go to one star, and then the generations to go to another star, and then the velocity dispersion in the disk does the rest for you within timescales of 10 million years or so, or a galactic rotation. Then you actually have civilizations that are spread throughout the galaxy, whether you like it or not. So it seems to me that in terms of the physics, in terms of the engineering, such advanced civilizations are possible. And another thing which is argued, and which basically I said there, is that the time to go from this transition from a type 2 civilization to a type 3 civilization is considered to be quite small, partly because of this velocity dispersion of stars in the disk of the galaxy. Okay, so how could we detect these advanced civilizations? Well, one way is to look at the kind of signatures that they might produce. And in particular, what many people have discussed over many years, in particular thinking about the Dyson spheres, is that these civilizations, if they have extraordinary energy requirements, because, for example, they want to go from one star to the next star, then they probably also produce a lot of waste energy. And in particular, even if they're very efficient, they'll produce waste heat energy. So, I mean, we do this all the time, and it's partly because this is really a fundamental aspect of physics as we understand it. These are the first two laws of thermodynamics. So the first law is that energy is conserved, and the second law is that if you have a closed system in which no one interferes, then the entropy in that system, the disorder in the system, always increases. So, for example, energy typically will change from a very concentrated, focused form. For example, the petrol or the benzene in your car, to a very sort of disordered and very diffuse form. So the heat that engine produces, these are the kind of basic laws of thermodynamics, and they're very difficult to get around. It's very difficult for this not to happen. And I think we're familiar with this in our daily lives. If you look at infrared cameras, then you see that we produce a lot of waste energy. From laptops, for example, from the emission from power stations, and here car engines, etc. Whenever we use energy, then there's always waste heat produced. It's difficult to get around this. This is the basic laws of physics. You can be very efficient with your energy use. You can create very large radiators to try and radiate the waste energy, but in the end, there's always some residual waste that's there, and it's difficult to hide. So, if you look at what temperatures, for example, that waste energy might emerge at, then there's certainly probably an upper limit. If you had a civilization that was very careful to try and radiate its waste energy at the lowest possible temperature, well, one limitation is that the radiators have to be solid. They can't be melting, right? So the radiators have to be solid. So that kind of puts an upper limit on the temperature of the waste energy that they would be producing. If you look at, for example, the thermal emission that we see from nature, but also from our own energy use, then you see that, for example, here, a power station, the waste heat that you will see if you look along a transformer out there in the streets that produces energy, typically is a temperature of about 300 Kelvin or so. And so most of the emission, if you look at that, then most of the emission, the thermal black body emission, comes out in the mid-infrared or in the far infrared. If you have a very efficient system where the waste energy was coming out at 50 Kelvin, for example, which is just about as cold as it gets in the Milky Way, in the star-forming clouds where there's a lot of dust in the Milky Way, then we would expect most of this waste energy to appear in the mid-infrared, and if these aliens are very, very clever, maybe in the far infrared part of the electromagnetic spectrum. So, how could we detect this? How could we detect this excess heat from galaxies, for example, from type 3 civilizations, very advanced civilizations that are producing huge amounts of energy? We would actually expect to be able to detect these in astronomical data. And so this is one of the things that I've been working on over the last year or so, is that there's a well-known correlation for a galaxy between the emission it produces in the radio part of the spectrum and the energy that it produces in the infrared part of the spectrum. And I don't want to go into the details of this, but it's essentially because both of these emissions are associated with star formation, so the formation of stars. The more stars you produce, the more infrared emission you produce, and the more radio emission you produce. This is a completely natural phenomenon, and we see it very strongly in all the galaxies. So, for example, these are some local galaxies in the nearby universe, and there's this very strong correlation where the ratio between the energy being emitted in the infrared and the energy being emitted in the radio is roughly a factor of about 100 or so in the far infrared part of the spectrum. So that's interesting because if we assume this is just a natural ratio, then what we can do is we can look for outliers. We can look for those galaxies in which the infrared emission is actually much, much brighter than we would expect just from a natural astrophysical explanation. So that's one of the things that I've been doing. So this is just this ratio of the infrared to the radio, factor of about 100. And you can see that there are some galaxies where the ratio is actually much larger than we would expect. So rather than a factor of 100, it's actually a factor of 1,000 between them. And so these systems are, in fact, candidate type 3 civilizations. Now, don't get too excited. Because it turns out that when you look at these outliers in the far infrared and the mid-infrared correlation, you look at 100,000 galaxies, and actually there's only a handful of them that has this very high anomalous mid-infrared excess. And if you look at them, and you look at them across the electromagnetic spectrum so that you can understand them and how they work in really a lot of detail, then it turns out that they all have fairly mundane astrophysical explanations, which is disappointing, but that's the way it is. Also, there's another global scaling law in galaxies called the Tully-Fisher relationship, which is if you plot the optical brightness of a galaxy against essentially the galaxy mass, it's actually the velocity at which the stars in the galaxy are rotating. But if you put these two things together, then you also find this correlation. Again, you can go and look for outliers because, for example, if you have a type 3 civilization, and if they're using their stellar energy as an energy source, which would be the thing to do, stellar energy is a fantastic resource, in fact, then you would expect them to be you'd expect them to be absorbed in the optical because you're collecting so much of the starlight for your own purposes. So these are outliers in this correlation. And again, I have to disappoint you that when you look at them in more detail, they all have regular astrophysical explanations of why they are not on this correlation. So far, I think it's fair to say, and maybe you're not surprised, because type 3 civilizations do sound a bit like science fiction. So far, there's really no evidence in astronomical data for the presence of type 3 civilizations in the galaxies that are in the nearby universe. The nearby universe is something like 100 million parsecs, so it's 100 million, roughly 100 million light years from the Earth. Okay. one interesting thing, so we haven't stopped using this technique, but this fact that the infrared and the radio are correlated with each other, this doesn't just happen in terms of looking at the overall brightness of a galaxy. This correlation also holds if you look on the subgalactic scale. Then there's always this nice correlation between the radio and the mid-infrared, which means that we can actually begin to look not just for type 3 civilizations using this technique, but we can actually begin to look for type 2 civilizations, or at least type 2 civilizations that have colonized significant fractions of the known galaxy. And that's something that we are hoping to do over the next few years. Okay, so message is that so far, at least my perception is that type 3 civilizations are something that are not out there, not easy to find, at least in the local universe. What about type 2 civilizations, right? It's less science fiction in a sense, because the energy requirements are sort of not quite similar to what we know and use ourselves, but they're not so different. What can we say about type 2 civilization? Well, I go back to the Kepler results, which we mentioned before. Kepler has been looking at 150,000 main sequence stars and basically detecting planets, because as a planet moves in front of the star, then because the planet doesn't emit light, then the brightness of the star decreases. Now actually it decreases very slightly, so even the largest planet will only decrease the brightness of the star by of order 1%. So it's a very difficult observation to make actually. And you can see, so here for example, this would be the typical signature that you might see of a planet. So a very small reduction in the brightness of the star overall due to the planetary system. Well, about a year ago, a lady called Tabitha Boy-Diano, I'm not sure how to pronounce that, but let's call her Tabby. She discovered this star in which you actually discovered, or you could see dips in the brightness of the star by an order of 20%. So this is absolutely huge and cannot be explained by a planet. The planet would have to actually be like a star almost to be able to, or a brown dwarf, to be able to produce such a dip in the light curve. And on top of that, you also see that there's fantastic structure. When you have a normal planet, then you have this very nice symmetry for the light curve, typically. But here you see all sorts of structure in the dimming of the brightness profile of the star. So this is certainly a very interesting object. And the astrophysical explanation for this is that can't be planets, so what else can it be? Maybe it's some cometary fragments or the breakup of a cometary system, which is plunging towards the star. And we just happen to be lucky enough to see the dust from these comets actually obscuring a significant fraction of the star, so 20% of the star. It sounds pretty far-fetched, if you ask me, and I think most astronomers also find it a pretty far-fetched explanation. So maybe we're missing something. But the other possibility that Jason Wright, for example, has come up with is that could this actually be a type 2 civilization? Could this be the signature of a type 2 civilization where 20% of the star is being occulted by this sort of mega infrastructure, alien infrastructure that's been built around the star to take in the energy from the star and to do whatever it is that type 2 civilizations do. So I think this is very interesting and certainly gives us some hope that if type 3 civilizations perhaps are not realistic, then perhaps, so far, perhaps type 2 civilizations are. This is a type 0 civilization. There's nothing really strange about this. It really does happen. So this is, for example, or we couldn't really call this a mega structure, but this is the International Space Station and the Space Shuttle. Dimming out, actually, I don't know, probably 10 to the minus 20% of the star's sunlight, but because we're so close to it, we can actually see it.
So, you know, this is not science fiction. Maybe the scale is science fiction, but the phenomenon itself is not really science fiction. Okay, there are a few things that are very interesting about Tabby star. It's the first star that has shown this very complicated light profile, this very complicated dip of 20% and all the structures that we see within it. So we've looked at 150,000 main sequence stars, and this is the first time that we've seen anything of this kind of nature ever before. So even if this is a type 2 civilization, it implies that type 2 civilizations are probably very rare in the Milky Way anyway. The other thing which is really difficult to understand is that, as I mentioned before, when you have dust, for example, and you have it surrounding a star, so the cometary dust, for example, here, it has to be really far away from the star for it not to be heated up and not to give out mid-infrared and far-infrared radiation. And there's absolutely no excess of mid-infrared emission from Tabby star, and that's also a problem for the type 2 civilization. You would also expect it to be warm, to be producing waste heat, and we don't see any infrared excess. So I think this is really a conundrum, and I think it's one of the most exciting areas in astronomy at this point in time. People are looking at this star with every instrument they can think of, so hopefully within the next 12 months or so we'll get a better idea of what's actually happening here. But at the moment, type 2 civilizations are not ruled out by this observation. Okay. Now, I don't want to be even more pessimistic than I've been so far, but, you know, about 70 years ago, Enrico Fermi asked this question, where are they? So where are these aliens? You know, if there are so many planets in the Milky Way, there are so many galaxies, there must be conditions for life. If life arises whenever the conditions are correct, if intelligence isn't that rare, then, you know, we should have seen the signatures, we should have had evidence here, even in our own environment, for type 3 and type 2 civilizations, and we don't see any of that. And I think it's particularly pessimistic. If we look at the solar system, for example, you don't see anything like this. You don't see any artifacts that are left over from visitors. The solar system is absolutely pristine. It's absolutely pristine, and some of these places, for example, you don't have erosion the way you have here on Earth because there's essentially no atmosphere. And so things could actually have been pretty well preserved. So if you look at Mars, I mean, some people get excited about Mars. I have to say, I don't get excited about Mars at all. And it's really kind of dull. And maybe there's something under the surface, but the surface itself is absolutely sterile. It's bathed in UV radiation from the sun. There's nothing there. You know, it's as sterile as, you know, the hospital down the road we go. It's actually more sterile. Much more sterile. But okay, Mars. But we all got excited by Ceres, for example. You know, the Hubble Space Telescope took images before the Dawn spacecraft got to Ceres. And we saw this white spot, and everyone got really excited. I got excited about it from here. Maybe this is the first evidence for some artificial I don't know, base or something like that, or some alien artifact. In any case, I was still excited when I saw this. It still looks pretty good. But then when you see the most recent images from the Dawn spacecraft, you see that this is actually a sort of salt that's coming out from these craters of geological structures in this dwarf planet. So Titan, absolutely the same. You know, this has an atmosphere. It's almost considered to be perhaps a primordial atmosphere that perhaps we had here on Earth billions of years ago, but absolutely no evidence that there's anything there or that anything has ever been there. The Rosetta comet, of course, and we think that comets and asteroids would be places that civilizations, including our own, would use to be able to get raw materials, to build infrastructures, to fuel our starships or whatever. Again, absolutely no evidence that these have ever been visited. Pluto, fantastic picture of Pluto, but again, you know, absolutely nothing there except what nature intended. But I have to say, I find that very impressive in some way, very disappointing, but also very impressive that the solar system happens to be absolutely pristine as far as we're aware. Okay, what about the future? What about looking for type zeros and type 1s? And in some senses, these are more interesting because they're closer to our types of civilizations. They may not travel to stars, for example. So it may well be that, you know, they don't go out to other solar systems and they don't start landing spacecraft in all their planets and all their moons, etc. So perhaps this is the place that we should be focusing on. And in fact, in the future, it's certainly possible that we can do some interesting things. This is the European Extremely Large Telescope, for example. Here, you couldn't say anything about intelligent life, but by looking at the spectra of exoplanets, this is the sensitivity to be able to do that kind of spectroscopy, then you could look for the signatures of life. The signatures for life are principally oxygen and ozone. It will be possible, hopefully in the future, with the nearest stars, to be able to do some of this kind of spectroscopy on the exoplanets that are around it. So that's one thing we can do in the future. The other thing we can do is looking for artificial communication signals. I said earlier that it's very difficult to detect radio signals from civilizations like our own, but in fact, with the telescopes we're building now, we can do better than ever before. So for example, the SKA will be so sensitive that it will be able to detect just a normal airport radar, a military radar system, out to 50 light years away. Actually, it's still our cosmic doorstep, but it's much better than we can do at the moment. So there's hope that as our technology progresses over the next 10, 15, 20 years, that both in terms of the ELT and the SKA, that we will be able to do some interesting SETI for these much less advanced civilizations. Anyway, I was being pessimistic, and being pessimistic, you have to ask yourself this question. And personally, I really hate to ask this question because I have certainly been brought up, and I think generations of scientists have been brought up for the last 400 years to think that there's nothing special about the Earth, that there's nothing special about the solar system, there's nothing special about our position in the Milky Way. You know, this is the Copernican principle. It's a principle that's very much ingrained within physicists, that there's nothing special about us, there's nothing special about our planet, that we are just one example of something that is widespread throughout the Milky Way, for example, and throughout the universe. But you know, there are some people, and I think we have to look at it, that would suggest that there are things which are special about our planetary system. And if you ask the exoplanet people, they will also tell you that the solar system is unlike the exoplanetary systems that are being detected around other stars. In particular, super-Earths, so planets that are much larger, not much larger, but a factor of a few times larger than the Earth. We don't have any of those in our own planetary systems, but in exoplanetary systems, those are found very frequently. And this is actually a good thing. It makes us different, but it's a good thing because those super-Earths probably are places where, if they're in the habitable zone, they hold on to their atmosphere, they hold on to their water. There must be plenty of water in these systems. Probably very good places to search for life, but it does highlight that our own planetary system is somewhat different from the planetary systems that we've detected so far with Kepler. There are some biases in what Kepler detects, but overall it seems that there may be something actually a little bit special about our own planet. So perhaps that's an explanation that, you know, life really is very rare, or at least intelligent life is very rare, and we just happen to be in the right place at the right time. I would like to think that actually this is the explanation, and that we're just actually too stupid to see what's under our noses, that there's some kind of cosmic selection that doesn't allow you to detect advanced civilizations until you yourself are advanced enough to be able to kind of deal with the whole idea of other civilizations. And it reminds me of Van who, of course, famous Dutchman who invented the microscope. And in one day he discovered the biological, microbiological world, bacteria. No one knew anything about bacteria, even though they had a substantial impact in everything that happened to people, all the diseases, etc., that were taking place. Until this guy discovered the microscope, we had no idea of a whole new universe of bacteria. And of course, bacteria have been here around on the Earth longer than we have, and they're probably one of the prevalent forms of life on other planets. But in any case, maybe this is where, maybe this is a reason that we haven't discovered civilizations outside of our Earth. We haven't reached that level of development where it's required, and there's some kind of cosmic censorship in there. You know, the universe is a clever thing, and somehow it stops us from understanding this until we're clever enough to be able to appreciate it. This is also maybe on the same theme as, you know, humans have a very, very strong preconceptions of how things should be. When we do science, we have a very strong preconception. Maybe in the future, and maybe this is the sort of step that, sort of a railroad step, is that when we have cognitive computing, when we have computers that can almost think for themselves, that don't have the bias that humans have, that maybe this is the kind of technology we require in order to be able to detect other civilizations. I'm kind of running out of time, so there's also the fact that there's the idea of the great filter, that we have many civilizations and life is widespread throughout the Milky Way, but we never reach an advanced civilization, a type 1 civilization, or type 2, or a type 3 civilization, because there's some sort of filter that we all come up against. For example, in our case, it could be the fact that, you know, we blow ourselves up in a nuclear war, or we continue to overpopulate the planet and we can't feed ourselves, or we continue to fight over oil or whatever, and we self-destruct. So the great filter is also perhaps something that's interesting. And of course, in our case, we don't know whether we are here in terms of the great filter, or whether we may be here and uniquely moving beyond the great filter. That's something that we will discover eventually, one way or the other. This kind of summed up, I think, where I have to see far. Two possibilities exist: either we are alone in the universe, or we are not. Both are equally terrifying, and I think that's actually very, very true. I want to finish off with some conclusions. I want to go back to the longevity of a civilization. I think that's clearly important in terms of being able to detect other civilizations. The longer civilizations live, the larger the chance we have of actually being able to detect them. And it may be that the reason we don't detect these civilizations is that indeed we have very short lifetimes, and we all run up against the same problems. This is another nice cartoon I like. The bad news is you've got advanced stage humans. The good news is they're just about to run their course. So that may be the case for every planet that takes life. So just to wrap things up, one lesson that perhaps we learn from SETI research is, you know, that we don't have these advanced civilizations, at least we haven't detected them so far. That we should start looking after our planet, start thinking about the future, thinking about sustainability. That we should look after each other, and that we shouldn't just look after our friends, but we should also be looking after our neighbours. We are all global citizens. We all have to look after each other if we want to have a civilization that will actually live long enough so that we can make a fantastic discoveries of the future. I'll leave it there with my conclusions, and I'm happy to take questions. I'll also take questions in Dutch or English, whatever you want. Thank you.
Yes. What can you tell us about the wow signal that they found in 77? The 72-second signal that wasn't repeated?
So,
Was it comets?
yeah, I don't think it's a comet. No, I'm very skeptical of that idea. We've never detected radio emission from comets at that particular frequency. It's the frequency of neutral hydrogen. So I'm very sceptical about that. What I could have talked about is the transient radio sky. At the moment, we're just beginning to understand the transient radio sky, and one of the things we've discovered just over the last few years is that about 10,000 times every day we have these very bright flashes of radio emission. They last for about a millisecond. They're all over the sky, and we have no idea what they are. There are some which repeat. They come from the same position in the sky, so they might be giant pulses from pulsars in nearby galaxies. But there are some that don't repeat. They're probably really extragalactic, really cosmological. So far, I don't believe that we've identified the host galaxies of these flashes. So perhaps the WOW signal, for example, was something akin to that. But I don't think it's a sort of two comets coming close together. Yes.
This whole thing about type 1, 2, and 3 civilizations, well, of course it is science fiction, but it's also kind of inexplicable. Why would a civilization even want to harness the entire energy on Earth? I mean, I was hoping we're going in the other direction a little bit and conserving energy here, except for the purpose of maybe transmitting the signals for other civilizations, that is, if there is such a thing. Even that doesn't require nearly the amount of power. I mean, why would a civilization want to? I don't dispute that they might want to explore other stars and so on, but why would they want to harness that much energy? It's ridiculous.
At some level, I agree with you. I mean, I think there's an interesting argument, for example, that energy usage so far has been exponentially increasing for humankind, right? If you plot energy usage over the last 300 years, then you see that it's basically exponential and it's unsustainable, right? And so we're working very hard to use energy more efficiently. That's really what we're doing, rather than trying to produce more energy. As you say, we're trying to actually be more efficient with our energy. I think that's the case. But I think also that if you want to be able to communicate, if you are spacefaring, then you need energy in order to be able to visit the nearest stars. So that at some level you need more energy than we certainly have at our disposal at the moment. And the other thing is that you want to communicate. If you do have a colonization program, then you want to be able to communicate across large distances. And so in order to be able to do that, I think we want to be able to send very powerful signals. Because if you don't do that, you don't have the bandwidth by which to communicate.
Or directional signals. Or directional signals.
Yeah. Well, even directional signals, they need to be powerful signals in order for you to be able to pick them up with.
Well, it's a trade-off.
One of these.
Well, it's a trade-off. If you could build something as big as to surround the star, then you could make a pretty large parabolic dish that would communicate with
You have one of these. You don't want a parabolic dish attached to it, right? I mean, you want a simple antenna in order to be able to communicate. Okay, but at some level I agree. Yes.
First of all, thank you for the inspiring lecture. I was wondering, the evidence you talked about for the type 2 civilizations, if I understand correctly, is the measurement of the energy warmth that is increased by 1 or 2% in the star. And how you know that that is not the normal fluctuation of the star, you know, fluctuation in energy or what?
Well, these are main sequence stars. So the stars like the sun, for example, and so the changes that they undergo are minimal. So a planet actually crossing in front of a star is actually much more significant than any of the jitter that you would see in a main sequence star. It's just, I mean, stars are big things, so it's difficult to make them change, even if you want to. It's difficult to get them to vary really quickly because they're so large. So they're actually relatively stable compared to a planet actually passing in front of the star, which is a significant decrease in the, well, 1% decrease in the stellar output. I mean, having said that, if you look at our own star, the sun, and you're close enough, you see fantastic dynamics of the energy, but the overall output remains more or less stable. Yes?
We'd be looking more, shouldn't we be looking more at dwarfs, like a rainbow coffin than stars like ours?
Yeah, I mean, I think this is there's always a suggestion in the sort of SETI research about what you should be looking for and what your strategy should be, what's the best strategy to find, SETI civilizations. And I guess this is the recent one that you should look at red dwarfs because they are very long-lived compared to main sequence stars like the Sun. Essentially, they live, well, not forever, but they live much longer than main sequence stars. So there's much more time for evolution to start on planetary systems around those stars, much longer time period for life to arise. So yeah, I think, I basically think there's been so many theories over the years about what's the best thing to look at, is that I think we should look at almost everything. I don't think we know enough to say what's the best strategy. Some people want to look at the galactic center because there's a huge density of stars. Some people don't want to look in the galactic center because they think it's far too violent place to look at. I mean, everyone has their idea, but I think those ideas are almost a fashion, and they seem to change on timescales of fashion as well. I mean, the other problem with the red dwarfs, of course, is that they also have these flares, so that if you have and the stars have to be, the planets have to be closer into the star to be in the habitable zone, where liquid water would be on the surface, and so they would be more prone to flares from those stars, which, for all we know, that might actually be good for life, right? I don't know. It might mean that you have a really dynamic evolution of life and you get really advanced civilization. But certainly it would be damaging for us to be there on those kind of planets.
It occurs also more often on red
Sorry?
dwarfs. It's more often occurring than the flare.
Yeah, red dwarfs have their flare stars and flare stars, they flare up often. Yeah, and the planets have to be closer to the star in order to be in the habitable zone because it's less cloudy.
Just to make sure, the 20% decrease by tech, this was seen only once and only for this.
No, there's I think it's the case that's only been seen once. I need to be sure, but there's two incidences separated by a few hundred days where you had massive. Not all of them, both of them were 20%, very close to 20%.
So twice on Teddy, or are there other stars where you see this?
There's no other stars that have shown this kind of significant decrease in the brightness. And, Kepler's monitoring 150,000, or at least it was monitoring 150,000. So people are trying to look at Tabby star again using other instruments to try and find more of these, because actually the decrease is so small that it's relatively easy to detect these.
And then let me ask another question. So I understand that you are looking for other life in terms of higher infrared radiation. But what about if you have a new civilization which also has new technology which provides a much better use of infrared in terms of energy, then you won't detect anything?
Yeah, well, it's kind of possible, for example, maybe an advanced civilization rather than, maybe it can somehow be so efficient that the waste energy doesn't go out in the mid-infrared, but actually goes down into the far infrared, for example. Or even maybe somehow they get rid of the radio. It doesn't seem likely, because what is the gain for that society to be so efficient? The efficiency gain is actually, you go from 99% to 99.9% efficiency gain. You actually need to quadruple the size of your radiators, for example, or lower the temperature by the fourth power. So,
But you understand, obviously, also energy is so extremely costly, and all these high-tech civilizations, as we want to use it as efficiently as possible, which simply means there's a technology driven towards the fact that I also use the infrared.
could be.
Success.
Yeah.
In which constellation can we find Lente?
So this is in Cygnus, I think. Yeah, Cygnus. So Kepler basically stares at a region around Cygnus, so about 20 hours right centre, 40 degrees declination, something like that.
Yeah, I was just curious because you were talking about the outliers and then saying that there were astrophysical reasons for it.
Yeah.
Could you give an example of that?
So, look, I can switch back to it. Yeah. Yeah. So for example, all of these objects, actually it's only one object, they all have an excess in the mid-infrared. And if we look at the data from other wavelengths, then we can work out that actually what we have here, for example, is an active galaxy. So this is not a normal galaxy like our own galaxy. It's a galaxy where in the center you have, for example, a supermassive black hole. We have a supermassive black hole in our own galaxy, but it isn't being fed by very much material at the moment, so it's kind of dormant relatively. But there are other galaxies, especially as you go to the distant universe and you go to earlier epochs, where you have a black hole that's being fed by inflowing matter. You know, there's a lot of gas still around because they're younger galaxies and they're forming stars, but also that matter that forms the stars also ends up circling the black hole, and so you get, they become very bright. So that's an active galaxy, and that will produce a lot of infrared if it's surrounded by a lot of dust, for example. And so that doesn't fall into what we call normal galaxies like the Milky Way. This is an active galaxy. And another way you can get it is what we call sort of nascent star formers. So this is where the star formation has just happened. And when the star formation has just happened, then the radio emission lags behind the mid-infrared emission. The mid-infrared emission comes out first. Again, it's dust around the stars. So you have starlight, you have dust. The starlight gets reprocessed into the mid-infrared. Well, the radio emission, which is associated with supernova, so you have to wait until those stars go bang, that radio emission lags behind the infrared, so that's the reason you can get this high, it becomes an outlier. So those are the kind of astrophysical explanations.
I'm afraid we're out of time for further questions.
Okay.
On behalf of the astronomers who speak F.Kaiser, we would very much like to thank you for your lecture.
Okay, thank you very much.
We also have this commemorative mug, which I should say is also on sale in some
Okay, thanks very much.
Thank you very much. Before we will leave, I'm not as out of breath right now, so maybe now I can make it clear how the tools work. If you've booked before, then you have a ticket for it. If you haven't booked it, or if you would like to do one, then you can buy one downstairs in the same shift as this lovely mug. We will, well, you can go back to the reception room where you were earlier. You can drink a coffee, discuss, is there alien life? Maybe there is. Would you be there, or would you?
Yeah, I need to see what my partner's saying. I have to do what she says, so I might be around for a while. Yeah.
Okay, so maybe you can ask further questions to Professor Garrett. And I would like to thank you all for coming. Those of you who were at all the lectures, or most of the lectures, thank you very much. But also those of you who were here for the first time, thank you very much. Hopefully next year we're organizing the series again, so be sure to tune in. I'll also send an email to all of you and all the other guests at the other lectures with the videos of this lecture and all the previous ones, so you can enjoy them again at home. So let's thank you, Professor Garrett again.
Professor Garrett, once again, very much thank you for your lecture. Also, as you may have noted, this lecture was the last in a series of 4. For this has been organized and put together by a very dedicated committee which has worked on this for the past few months. So on behalf of F.Kaiser, I would also like to thank the organizing committee. members sadly can't be here today, but the other committee members are all here. So I would like to thank Olivier. Well, thank you very much for your effort. There you go. There you all go. Well, thank you all very much for coming. Once again, thank you, Professor Garrett, for your lecture.